In this video, we are going to look at higher order derivatives and what that means for the shape of the graph.
Let's start with looking at a real-life example. If f of t represents the distance we've traveled, then the derivative of f of t is the rate of the distance traveled, or rate of change in the distance traveled, which is your speed or your velocity. So if we're thinking of driving a car, the distance we traveled, that's how far we've gone. The speed is what we're seeing on our speedometer. This is how fast we're going. The second derivative is the rate of change in that velocity or the rate of change in the speed, and that represents the acceleration. When we are looking at these derivatives of derivatives, we have a couple of different styles of notation. So if we have our f of x function written in our function notation, our derivative we usually write as f prime of x. And if I'm writing the second derivative, I have two little prime marks. So the second derivative. If I'm using y equals notation, then I often will use the Leibniz style notation of dy dx for the derivative. And for the second derivative, this one looks a little bit funny, but we're taking the derivative of the derivative, and so we have d squared y dx squared. That's the second derivative notation. Let's practice taking a few second derivatives. In order to take the second derivative, we need to take the first derivative. So the first thing I'm going to do is I'm going to rewrite this function so that I can more easily use my power rule, because these two terms, the first and the second terms, are easy to differentiate, but this third one, it's helpful if I rewrite it so that power of x is in the numerator. So we're going to have x to the fifth minus 4x squared minus 3x to the negative 1. When I take the derivative, I get f prime of x, which is 5x to the fourth, minus, that's going to be 8x. And then I'm going to take the negative 1 times the negative 3, so that's going to be positive 3x to the negative 2. That's my first derivative. My second derivative, I'm just going to take the derivative of my first derivative. So I'm going to take the derivative of this term first. I'm going to have 20x cubed. I'm taking 5 times 4, that gives me 20. X to 1 less power. Minus the derivative of the 8x, that's going to give me minus 8. And then lastly, we're going to take the derivative of this last term. I'm going to take negative 2 times 3. That's going to give me minus 6. X to the 1 less, that's going to be minus 3 power. I cleared the screen so that we could have more room to take the derivative of y. So our y function, we don't need to do anything to rewrite. I can just start by taking the derivative. So dy dx is going to be derivative of the first term, that's going to be 2 times 3, that's 6x. And then the derivative of natural log is 1 over x. Now I'm taking the second derivative, so I'm going to need to take the derivative of this 1 over x term, and so it's going to be helpful if I rewrite that as 6x minus x to the negative 1. Now we're ready to do the second derivative, so I'm going to have d squared y dx squared. Derivative of this 6x is just 6. And the derivative of the x to the minus 1 gives me plus, because I have a negative 1 times the negative, x to the negative 2. There's my second derivative. Let's look at a couple of functions that are a little bit more complicated. Looking at g of x, I'm noticing that I have x times e to the x squared. So I'm going to need to use the product rule. I'm going to start out by determining what I'm going to use for my f and what I'm going to use for my g. So my f is just going to be that first factor, x. G is going to be e to the x squared. My f prime is going to be the derivative of x, that's just 1. My g prime, this is a little bit more complicated because I have that x squared in the exponent. So when I take the derivative of my g, I'm going to need to use the chain rule. taking the derivative of the e part just gives me e to the x squared, and then I need to multiply by the derivative of that x squared. That's going to be 2x. So my g prime of x is going to be f prime times g plus f times g prime. So this is going to be 1 times e to the x squared plus x times e to the x squared times 2x. So I'm going to clean this up because I need to take the derivative again. So I'm going to have e to the x squared plus, that's going to be 2x squared e to the x squared. This is my g prime of x. Now I need to take the derivative of that again. And looking at my functions that I've got here, I know how to take the derivative of this because I did that right up there. Taking the derivative of this, I'm going to have to use the product rule. To make things a little bit simpler, so I only have to think about sort of doing one differentiation process, I might factor out that e to the x squared. And when I do that, I have e to the x squared times 1 plus 2x squared. So I'm going to erase my product rule information up here, and we're going to do it again. So now we're going to take the derivative of my g of x again, but this time I'm going to have f is e to the x squared, and g is 1 plus 2x squared. So this here is my f, this here is my g. I need to figure out what my parts are, so my f prime is going to be e to the x squared times 2x. My g prime is just going to be 4x. So let's go ahead and write our derivative. So we're going to have f prime, that's going to be 2x e to the x squared, times g, which is 1 plus 2x squared, plus f, that's e to the x squared, times the derivative of g, which is 4x. Now let's take the derivative of this function. So to take the derivative of this, we're going to need to know which rule we're going to use. I've got a fraction, and so I'm going to be using the quotient rule. So that's my f, that's my g. So my f is 2w minus 1. My g is w plus 4. So my g prime is going to be 1, and my f prime is going to be 2. Plugging this into my derivative rule for the product rule, not the product rule, the quotient rule, I'm going to have dx, so it's using that Leibniz style notation, so dx dw is going to be, I'm going to put a big fraction bar here, I'm going to have a w plus 4 squared, and I'm going to take f prime, which is 2, times my g, which is w plus 4, minus f, which is 2w minus 1, times g prime, which is 1. Now remember, I have to take the derivative of this again, so it's going to be helpful if I simplify things a bit. This is going to give me 2w plus 8 minus 2w plus 1. So where did I get that? Well, this one, really, that doesn't change anything. I need to distribute that minus sign there, and that's how I get that. Notice these two w's in this particular case cancel out, and then we don't want to forget our denominator. So we have w plus 4 squared. So this just gives us 9 over w plus 4 squared. Now, in order to take the derivative of this again, I could use the quotient rule, or I could think of this as 9 times w plus 4 to the negative 2. And if I think of it that second way, the derivative is a little bit easier. So my second derivative is going to be d squared w, d squared x, dw squared. And I'm taking the derivative of this thing, so I'm going to need to use the power rule and the chain rule. So when I take the derivative of the w plus 4 to the negative 2. I'm going to bring this negative 2 down in front. That's going to give me negative 18. W plus 4 to the negative 3. And then times the derivative of what's inside. The derivative of what's inside is just 1. So my second derivative looks like negative 18 over w plus 4 cubed. Let's look at what the second derivative tells us about the shape of our curve. When we have a curve that has this sort of shape, we say it is concave up. And what's going on here is if we look at what's happening to our tangent lines, if I draw some tangent lines along here, it looks like we're starting out with a small positive slope here, and this is becoming more positive, and this is even more positive. What's happening here is my slope, my f prime, is increasing because we're starting out with positive, more positive, even more positive. This would also be true if I had sort of like this side. So if I had that sort of shape, here I'm starting out with a negative slope, less negative, 0, positive, more positive. This, on this type of shape, my f prime of x is increasing. When my f prime of x is increasing and it has this shape, we say the curve is concave up. So if my f prime of x is increasing, that means if I took the derivative of this f prime, that's our second derivative, my second derivative is positive. So when we have our second derivative is positive, this means our curve is concave up. Doing the same process with a curve that is concave down, here we have this sort of shape, and if we drew those tangent lines, we're seeing that we're starting out with a positive tangent line, then we have the slope is less positive, here it's close to 0. This trend, this is a decreasing trend. And this would also be true even if it went like this. So we're starting with a positive slope. We don't even have to start with a positive slope. It just has to have a decreasing trend. So as we move to the right here, our slopes are getting smaller. So when our slopes are getting smaller, our graph is concave down and our second derivative is less than 0. When we have a graph that has these sort of concave up and concave down shapes, first let's make sure that we can recognize what's going on here. So along here, our graph is concave up. It's also concave up over here. And in here, my graph is concave down. It's also concave down over here. So in this region, we're looking at it's concave down, and this over here, it's concave up, and over here, it's concave up. So the place where your graph switches from concave up to concave down, or concave down to concave up, like this point right here at B, we're switching from concave up to concave down. This is called an inflection point. Remember that over here, my second derivative is positive, and in here, my second derivative is negative. And so these spots where our graph switches from concave up to concave down, almost always, not always, we have that second derivative equaling 0. Sometimes we have the second derivative equaling 0 and we don't have an inflection point. But if we have an inflection point, there's two ways that that can happen. We can have our, well, actually 3 ways that can happen. We can have the second derivative equaling 0. We could have the second derivative not being defined. Or we could have the function not being defined, which also means the second derivative is not defined. So let's take our graph that we have here. We have the points A through H, and let's determine whether we have a positive slope, a 0 slope, or a negative slope, a positive second derivative, 0 second derivative, or negative second derivative, and then identifying which things are inflection points. So looking at point A, at A, it looks like we're at the bottom of that cup shape. And so at point A, we have a zero slope. We also know that our graph is concave up there. And so when it's concave up, we know that our second derivative is positive. And this is not an inflection point. At point B, function is headed uphill there, so that means my derivative is positive. And at that point, this is the spot where my graph changes concavity. And so I'm expecting my second derivative to be 0 there. And yes, this is an inflection point. At point C, again, we have a place where we have a horizontal tangent. And so my first derivative is going to be 0 there. My graph is concave down here. And so my second derivative is going to be negative. And no, that's not an inflection point. At point D, this point right here, my graph is headed downhill. So that means my slope is negative. And while it sort of looks similar to this point here, B, my graph is still concave down there. So my second derivative is negative. So one other sort of nice way to identify whether your graph is concave up or concave down is when the graph is concave up, the tangent lines always lie below the graph. When the graph is concave down, the tangent lines lie above the graph. So do you see how that's above? And if we draw in that tangent line at D, it looks like the graph is still below that tangent line. So this is not an inflection point. At point E, this is what's called a cusp. It's a corner. And when we have these sharp corners, our tangent line, we don't really know how to draw it in, because does it go like this? Does it go like this? Does it go like this? There's no way to really hug that curve like we want our tangent line to do. And so here my slope is undefined. And that means our second derivative is going to be undefined. And if I look at point E, over here my graph is concave down. Over here it looks like concave down, so it doesn't change concavity, so it's not an inflection point. Okay, let's look at point F. So at point F, we have a place where we have a horizontal tangent. So that means we have a 0 slope there. The graph is concave down, so my second derivative is going to be negative, and no, this is not an inflection point. Point G, here we have our curve is headed downhill there, so that means we have negative slope. G is that place where we have that inflection point. So my second derivative is going to be 0, and yes, this is an inflection point. Finally, at point H, again, we have that horizontal tangent, so we have a 0 slope there, and we have our curve being concave up there. So that means our function has a second derivative that is positive, and this is not an inflection point. Let's look at one example of how the second derivative can inform what's going on with a more real-life application. The following shows the total sales of a new product in millions of units, and we can see that our sales are sort of rising over the years, and T is time in years since the product was released. So this is T, and this is our S of T. First, we're asking, when is S prime of T greater than 0? So another way to say that is, when is S of T increasing? And it looks like the whole time it's increasing. So we're going to say 0 to 10. So the next question is, when is the second derivative greater than 0? And if I look at my graph here, along here, all the way up to about maybe there, my graph is concave up. So along here, it's concave up. And so I would say maybe 0 to 5.5. My second derivative is positive. Oh, whoops, I put it in the wrong spot. That's where it goes, 0 to 5.5. Now, what does this mean? Well, in this area over here, my S prime is increasing. So that means my sales are accelerating in that region. So in those first 5.5 years, the sales are accelerating. Now, the next thing it asks us is about, when is the second derivative negative? So where is my curve concave down? In this region, it's concave down. So that is from, say, 5.5 to 10. And in that region, my sales are decelerating. So our sales are slowing. So the last question we're asked, how many years after the release of the products were the sales selling the fastest? If we're trying to determine something about the rate of change in our sales and when were they the fastest, they're asking us basically when was the slope of that tangent line the largest. So when is that tangent line the steepest? There, right at 5.5, that's when our tangent line is as steep as it's going to get. Notice that's the same place as we had that inflection point. The places where your derivative reaches a max or a min, a high spot or a low spot, these are the places where your second derivative is 0. Those are the places where you have an inflection point. That's it for this video. Hope you found it helpful.